Welcome to another lecture in the Performance Analysis series. In this lecture, we will be discussing the fundamentals of the Venerable Message Passing Interface, or MPI library. We'll discuss blocking and non-blocking point-to-point communication, collectives as an ergonomic shorthand, and how to understand MPI communication performance. MPI is a standardized and portable message passing system designed to function on a wide variety of parallel computers. It is important to note that MPI is not a language, but a library specification that defines the syntax and semantics of a core of library routines. MPI informally refers to the software libraries which implement the functionality of the MPI standard, like OpenMPI and MPICH. These libraries can be called from C, C++, and Fortran programs to enable high-performance SPMD-style codes. Bindings in innumerable other languages build off these base implementations. As you may suspect from the name, MPI is all about passing messages. This means it is a communication interface rather than an interface dedicated to enabling computation. The MPI standard was developed by the MPI Forum, a group of researchers, computer scientists, and engineers who met to discuss and develop a standard for message passing libraries. The first version of the MPI standard was released in 1994. The most recent version, MPI 4.1, was released in 2023, and MPI 5.0 is currently under development. What we will discuss today is a high-level view of the foundations of MPI, including blocking send and receive operations, non-blocking send and receive operations, and collective communication operations. For this reason, older MPI versions should work just as well for this lecture. Before the advent of MPI, parallel programming was a bit of a mess. Each vendor had its proprietary method of sending messages between processes, which led to significant compatibility issues. The development of MPI provided a unified and efficient approach to message passing across different computing architectures. Why is MPI standard practice in scientific computing? How does it differ from other parallel programming models? What are the key concepts and terminology you need to know to get started with MPI? Imagine a company with a warehouse full of boxes has hired you to count them all. Doing so alone would be interminable. But if you had 20 friends to help you, you could divide the warehouse into sections, and each person could count the boxes in their section. Thus far, this is the standard argument for parallelism. Now, the warehouse manager is expecting the final tally for the boxes. You and your friends need to communicate your partial results in order to determine the total number of boxes. You need to send messages to each other to share your counts, and you need to do so efficiently to minimize the time it takes to get the final count. This is where MPI comes in. MPI provides an efficient, standard method for computers to communicate through message passing, enabling large parallel programs to run efficiently on supercomputers. Let's start with the basics of MPI. The basic unit of computation in MPI is the process. A process is an instance of an MPI program that is running. Each process has its own memory address space and can communicate with other processes by sending and receiving messages within a single machine or by passing messages across a network of machines. Yes, MPI is a sufficiently generic communication library that it can be used to scale from your laptop to nodes to clusters. In MPI, processes are grouped into communicators, and each process is assigned a unique index within a communicator. That's the rank. If we start an MPI-enabled program with 4 processes, the ranks of the processes in the default world communicator will be 0, 1, 2, and 3. The rank in MPI is an identifier for a process and is used to identify the source or destination of a message. It is used as an argument in many MPI functions. By default, all processes are in a single shared communicator, world, and numbered by rank from 0. In more complex MPI programs, we may have different ranks associated with a single process when accessed through different communicators. The first MPI function that must be called in an MPI program is MPI init. This function initializes the MPI environment and must be called before any other MPI functions. It's usually a good idea to call this function as the first line of your main function or as the first line of your program. The last MPI function that must be called in an MPI program is MPI finalize. This function finalizes the MPI environment and should be called after all other MPI functions have been called. It's usually a good idea to call this function as the last line of your main function before the return. A program that uses MPI must be compiled with an MPI compiler. In practice, this is a wrapper around a standard compiler that includes the MPI libraries and flags built in. For example, the MPI-cc command is a wrapper around a C compiler, for example GCC, that includes the MPI libraries and flags. For Fortran, the wrapper is MPI Fort, and for C++, it is MPI CXX. These wrappers are usually installed with the MPI libraries, so you should be able to use them without any additional installation. If you run MPI-cc-showme, you will see the flags that are passed to the underlying compiler. On my machine, it looks like this. Thus, the MPI-cc command is a wrapper around Clang that includes the MPI libraries, specifically OpenMPI 5.0.7, and the associated flags, -lmpi. On different machines, you may have dramatically different configurations for the MPI-cc command. Here is an example of a simple MPI program that initializes MPI, prints the rank of each process, and then finalizes MPI. When the above code is compiled with MPI-cc, it generates an executable. This executable is MPI specific, and launching it requires another wrapper, this time called MPI run. The launcher takes as an argument the number of MPI processes to run the program with using the flag -n or -nt. For example, to run the Hello World program above with 4 MPI processes, you would use the following command to first compile with MPI-cc and then run it with MPI run. Doing so should produce 4 lines, saying hello from rank 0, hello from rank 1, hello from rank 2, and hello from rank 3. You have just compiled and run your first MPI program. If you think this was suspiciously easy, or that it doesn't seem to do much message passing, you are correct. If run on a single machine, MPI run will launch multiple copies of the program in a round-robin fashion, while on multiple machines, it will SSH into each to launch the requested number of program copies. To understand MPI communication, it is essential to consider what happens during message passing. Imagine a scenario where we send the data stored in variable A from one process to another, receiving into a variable B on the destination process. When the MPI send operation is initiated, the data is passed to the MPI runtime library. The runtime library acts as an intermediary that manages the transmission. Upon receiving the data, the library contacts the next available connector, requesting that the data be sent, for example, across the network. The data then traverses through the network switch, which may route it through various network components, possibly including multiple switches or routers, until it reaches its destination node. This entire pathway is abstracted away from the programmer, but understanding it is crucial when optimizing the performance of MPI applications. Similar to the messaging abstraction, MPI defines a buffer as an abstraction over several different concepts. In practice, an MPI buffer is a pointer to a memory location that is used to store data that is being sent or received, and may refer to a user-level buffer, a hardware system-level buffer, or a network-level buffer in some circumstances. In MPI, all library calls are prefixed with MPI_, followed by a single capital letter. This is a convention that makes it easy to identify MPI calls in your code. The MPI standard defines a large number of functions, but in practice, most MPI programs only use a small subset. Many computational scientists go their entire career using only a dozen or so. The most basic of these enable point-to-point and collective communication patterns, and these form the foundation of all MPI-based codes. The primary function of MPI is to enable communication between processes. The simplest form of communication is point-to-point communication, which involves sending a message from one process to another. In MPI, these tasks are accomplished with the MPI send and MPI receive functions. These calls are blocking, which halts execution until certain conditions are met. In standard send mode, the message is either passed to the receive buffer, buffered in temporary MPI managed memory, or the call waits for the receiving process. The first two options return quickly, while the last option will block the process. The blocking send operation only returns once the sender is allowed to reuse the buffer without affecting the integrity of the MPI communication. The data being sent has either been fully transmitted or safely stored by the MPI system. Similarly, a blocking receive operation terminates as soon as the receiving process can access the buffer and read its contents. This ensures that the data is fully available before proceeding. Note that blocking calls are not necessarily synchronous. It is rarely the case that a blocking call will return when the receiving process has the data. Understanding this distinction is crucial, as it often causes confusion when analyzing performance in MPI applications. Likewise, MPI implementations use temporary storage to hold messages, allowing non-overlapping execution of computation and communication. The primary pitfall of blocking communication is that it can lead to deadlocks if not used carefully. Deadlocks occur when two or more processes are waiting for each other to release resources, resulting in a situation where none of them can proceed. This can happen when multiple processes are waiting for data from each other, creating a circular dependency. In this short example, we see that rank 0 sends its buffer to rank 1, and rank 1 sends its buffer to rank 0. The next command is the corresponding receive. Rank 0 takes the message and puts it in A, and rank 1 receives the message and puts it in its own A. However, neither rank will ever finish the initial send call. We have created a deadlock in our program by communicating a buffer too large for MPI to manage automatically. If, instead, we used the synchronous send, called MPI send, then we could manage a deadlock with a single integer instead of a larger array. In this case, the constraint of synchronous communication, a guarantee that the message is received for the call to return, requires that each process is waiting for the other process to progress to return. Since blocking communication can lead to deadlocks, various patterns for the development of MPI codes have been developed to mitigate the issue. In a typical classic MPI code, one might filter based on the rank of the sender or receiver, for example, by using MPI send and then MPI receive on even ranks, and MPI receive then MPI send on odd ranks. For programs coordinating an even number of processes, this guarantees that each process will always have a partner to communicate with, preventing deadlocks. For simple cases where only MPI send and receive are used, it is sometimes possible to avoid deadlocks entirely by reordering the communication operations, or better yet, by combining them into a single operation using MPI send receive. This call simply concatenates the arguments to MPI send and MPI receive and avoids the potential deadlock with minor modifications. MPI also supports non-blocking communication, which is denoted by the prefix I, standing for immediate, as in this call immediately returns. Non-blocking versions of MPI send and MPI receive are denoted by MPI send and MPI receive, respectively. Non-blocking functions allow computation and communication to proceed concurrently, improving performance in large-scale applications. These calls initiate a communication operation and return immediately, allowing the process to continue. The trade-off of immediate mode communication is the need for verification. Since MPI does not guarantee that the buffers can be accessed safely as soon as the calls return, it is required to test that the communication completed before reusing the buffers. If it has not, this requires waiting. This is convenient if unrelated computations may be done in the interim, but relies on the structure of the program being amenable to these optimizations. Additionally, one nearly eliminates the potential for deadlocks at the expense of hammering the MPI library. One may, in principle, organize the communication of arbitrarily many processes through strictly point-to-point communication. In practice, we rely on the MPI implementation of collective operations. Some of these collective calls are one-to-many, many-to-one, or many-to-many. Likewise, some calls are strictly synchronizing, some manage communication, and still others enable multi-process computation. One-to-many calls include the broadcast and scatter operations for scalars and vectors, respectively. The many-to-one gather inverts that scatter operation, collecting bits of an array from multiple processes into one. The reduce call enables computation of a single value from those on many processes. All-to-all calls manage the interaction of all processes with all others. MPI includes a barrier call to synchronize a communication, by default all processes. This is used primarily when interfacing MPI with procedures that are opaque to the MPI library, often on-node file output. All gather and all reduce are analogous to their gather and reduce calls, but these apply to every process. Generally, the collective MPI calls are used sparingly. These can become a significant bottleneck in a high-performance program. MPI is a standard tool for the development of parallel applications. Today we've discussed the classical elements of MPI, including blocking and non-blocking point-to-point communication, and collective communication. We discussed the basics of writing, compiling, and executing MPI programs, as well as some of the pitfalls new MPI programmers frequently encounter. Thanks for watching. I'll see you in another lecture.